starting the lightning talk about how to model stability of the financial network with some methods of quantum computing. Probably, I think everybody from you know the financial crisis from 2007 or 2008, when, for example, Lehman Brothers or other banks went down and crashed or was in the default. And of course, also a lot of European banks have very similar problems because there was some crash of financial stability. This was the global financial crisis. What was the reason? What was the root cause of this? We can discuss. But what is interesting and what I want to show you for you now, there are some methods specifically from, for example, from the statistical mathematics and of course statistical physics, which is called like the thermodynamical approach. How you can measure or maybe how you can predicate this kind of stuff. But usually when you want to predicate a huge large of parameters, huge large of the settings and input parameters, you need some good performance, computing performance, and on this level quantum computing can help you a lot. What is the financial network? Briefly, it's a network between the financial institution, any actors of the financial market. That means everybody which want to something to sell, which wants to something to buy, has some relationships with some liabilities, with some assets, and this kind of stuff, creating financial network. Thanks to globalization, you know, there are a lot of, let's say, mothers, daughters between the banks, between the financial institution. There are a lot of regulation on the market, of course. There are a lot of financial instruments, specific instruments like the derivatives, specific instruments like the securitization portfolios and this kind of stuff. All these attributes create this financial network. And in principle, this financial network, it's related with some relation, usually with some recurrence relations because they create some regular patterns and this kind of stuff. And of course, for recurrent stuff, we are able to model it somehow. You probably know many recurrent stuff can be manifested like the fractals, for example. But probably somebody from you knows the game of life from John Conway. This was the brilliant British mathematician which provided this game of life game. And this game of life, it's quite good example, so-called cellular automation. That means when you have some automate, when you put some rules inside, some basic rules, according to these basic rules, this automate can create very complicated structure. And this is also the situation when, for example, we can model this financial network, which is based with some simple rules to very complex structure. This complex structure can have this, let's say, manifestation. That means works like the fractals or very specific image patterns. And as you can see, these patterns very often also in the nature. For example, this underwater snail, somewhere from the Australia, has very similar structure like, for example, this kind of rule-based pattern. Of course, in the mathematics, you have, let's say, a huge land of the different images like this. That means you have fractals like the Sierpinski carpet or Vicek fractals like you see. Everything from this can be illustrated and can illustrate. Anyway, what I want to say is with these recurrent patterns, you have a chance to modulate this financial network, as I said. And for this, it's very, I think, useful to use this pattern from the solid-state physics, which is called the Ising model or Ising model. It's quite old model, classical model, how you can modulate, for example, the ferromagnetism or other physical methods and aspects from the solid-state physics. And in this case, you just calculate some, let's say, Hamiltonian, which is more or less the energy of the combination of the spin or combination of atoms and some sum of these atoms in the lattice. And you can use some standard thermodynamical approaches how to investigate some very common phase transitions or other changes of order parameter or this kind of stuff or any other, let's say, values and features in this kind of macroscopic states. And usually, because this is macroscopic state, which is based also on the lot of particles, and it's huge because contain a lot of parameters inside, what mathematicians or physicists using for this when they want to investigate inside, they are using so-called Monte Carlo calculation, because usually it's not possible to analytical calculate multi-dimensional integrals or sums with standard analytical way. That means they are using some numerical approaches. And this common approach is called Monte Carlo. What is Monte Carlo? It's on one side a synonym of the gambling, but this is not our case. In this case, Monte Carlo is called because they're using some stochastic approach. Maybe, for example, you know this example when you want to calculate with this numeric approach, like something like the number pi or p. It's very simple to do it. You will just use the normal distribution. You are shooting this kind of, let's say, paintball on your target with the hair cross. And you can calculate and afterwards create the ratio between the points generated inside the cycle and outside square. And this ratio create you number pi, for example. This is a simple explanation how Monte Carlo works. This is some, let's say, very specific distribution. It's uniform distribution. But usually, on different kinds of approaches, you have different also type of distributions. Especially, for example, for this model of financial network crash, we are using something different. How this is modeled? Asset and liabilities, you can represent like the spin particles with different spins, 1 or -1, depends what is asset, what is liability. Coupling constant can represent some mutual trading between assets and liabilities. There is also some parameters, extra parameters like the thermal coefficient, which represents some price fluctuation, which is interesting, especially when we want to investigate this kind of stuff like the stability or robustness of financial network, which can suppress some long-range correlation and completely disturb the ordering parameter in this kind of lattice. And because this thermal coefficient is something which is tell you about some critical stuff like the change of the phase state, usually in the solid state, but in this case, can tell you something about the stability or where your network going to some chaotic states, because change the long-range correlation. With this parameter, you are able to investigate, understand where is the situation when your financial network is not stable. And this is simple results. For example, these first results, when I'm using this fractal Sierpinski triangle inside, usually represents standard trading on the market, because this represents something which is called the Fibonacci series. And with this Fibonacci series, many traders work with this kind of stuff. That means there's very strong psychological, let's say, guide for the traders, how they trade on the markets when they want to trade or sell something. And they are using the Fibonacci approach. And you can see with this Fibonacci approach, the situation is quite different when, for example, on the right side, it's pattern which represents so-called securitization. Securitization is a technique from the economist when they want to, let's say, hedge some risk and this kind of stuff. And maybe you know, the securitization was also one of the root cause of the global financial crisis in 2007, 2008, because they have some, let's say, securitized mortgages, bonds, and this kind of stuff, and was not valid, this kind of stuff. That means you can see directly on this chart, for example, how this pattern can impact this problem. That means slow down and decrease the scalability and robustness of the network. Okay, quantum Monte Carlo briefly, it's a situation how you can improve this calculation. As I said, there are two main approaches. One is called variational method for the Monte Carlo, another is called the diffusion. And all these things works on the regular quantum computers. That means we need to hardware for this. But anyway, on the technical level or theoretical level, we are ready to implement it and work with this kind of stuff. That means everything like this was based when you have more questions and you need more answer on this article published in this journal. And I am also available to answer your question. Unfortunately, I have no time much more. That means everything from my side.